Hey Sarah. Sarah, how are you doing? My all-star student, one of my top 34 students. How are you doing today? Pretty good. Let's see. How am I doing? I'm okay. I'm very tired this morning. I had a super weird dream last night, and it wasn't bad, but it was so immersive that I think yeah, it wasn't a very restful sleep because I was very invested in the narrative structure of the dream. Hello, Ainara. How are you doing today? Thanks, Sarah. My apartment's a bit of a mess right now. I'm just trying to get everything in order, but it's a little difficult to do so right now. Hey, Justin. My apologies for being late. I messed up some eggs and burnt some stuff. Oh, classic. Becky, good morning. Chris, good morning. Woo! Let's see the subscriber count to see where we are with the reveals. We have 131 subscribers. We have 69 more subscribers to go until I forgot what reveal I was doing it. I think it was the instrument reveal at 200 subs and extra credit reveal at 300 subs. Hey Alex, good morning. Hello, Chris. Let's start when the live timer hits 5 minutes. So that's roughly around like 10:26. I want to go over two important things today. And then we can kind of move on from there. Okay? So get pumped. Oh my goodness. Good morning you tomorrow. I'm going to make some lemonade. I'll be right back. Delicious. All right. Congratulations, you guys are almost caught up with my Regents class. You're only like 4 days behind. when we first started this, we were a lot more behind, and we fell even further back because of the APs and stuff. But now we're really going at a fast pace. Right? Cool. So here we go. Today we're looking at 2D waves. Okay. And Eric, are you in the chat? Because today we're going to be working with a bird's eye view. Right. So in order to, we're no longer looking at for a water wave, like the cross section of the water. If your eyes are at water level, like this, my hands are the water level, you're no longer looking at the waves like this, right? You're no longer looking at one-dimensional waves on a string. We're looking at waves in 2 dimensions, so you want to see how they propagate all over through a 2-dimensional space. And for that to happen, we want to see a bird's eye view, okay, of a lake, right? So of water waves. So pretend you're at Central Park, which according to one Atun Chowdhury, the best park in New York City, okay? Or maybe you're at Riverside Park by the water, or the East River Park by the water. And I'm pretty sure Prospect Park has a pond as well in Brooklyn, okay? And you dip your finger in the water, okay? So you just boop, 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 right? And so if I poke my finger there, right, what happens is I create a circular wavefront, right, which is basically a circular crest and a circular trough, and it is propagating radially from where you dipped your finger, right? So it looks like this if I dip it multiple times, right? So this is what's known as a circular wavefront. Cool beans, okay? I think, I'm going to switch colors to blue because this black marker is running out of ink. Hashtag GoFundMe. Hashtag I don't get paid enough for this. Anyway, so I'm in a fantastic mood if you can't tell. Okay. Hello everybody. I missed you guys. Here's a big hug from me to you. Wow, that's me tapping the back of my laptop. Wow, so good to see you guys. Okay. So that's a circular wavefront. That's what happens when I poke my finger back and forth. So the trough would be here and here, in between those crests. Okay. There's a second type of wavefront. Thanks, Chris. Oh, word of caution, guys. Now that it's nice outside, especially to my fair-skinned beauties out there, Itamar, Alex, all right? Wear some sunscreen, okay? We're gonna learn about why that's important when we go over light waves and stuff next week. I usually pair it with the lesson on light, but we're going at a little slower pace this year, and summer has arrived sooner than we're going over light. So get some sunscreen, okay? Preferably 45 or greater, all right? And yeah, I care about you guys. Anyway, so you'll notice that not all waves in water look like circles. Some are flat, right? There's a wall of water. Those are the ocean waves we're more familiar with. And if you think about it, how real is SP? Itamar -1. It is very real. You want to be a conspiracy theorist? Itamar, how sick are your sock tans when you run in the summer? I remember when I used to run, holy moly, my feet would be so pale compared, right? And if you wear the little ankle socks, right, that tan line right there, It's like your ankle and everything is like super dark, and then like your feet are like so pale. The watch tan. I never ran with the watch. Yeah. Good morning, Yona. Good morning, Arnava. Wait, I already said good morning to you. Good morning, Yona. High five, Yona. Are you ready? 1, 2, 3. You know what helps the burn? You know what helps the tan line? Sunscreen. Anyways, so if you want to talk about how a flat wave is generated, all that is getting lots of different circles and poking them all at once at the same time, right? And that's how I generate a flat wavefront. So flat wavefronts operate in the exact same way, like crest, trough, crest, and they go in this direction, right? Or this direction. Depends on like how I look at it, right? Okay. So where am I getting with this? I want to go over the first thing, okay? And today's lesson will be all about how waves interact with boundaries. Okay, what is a boundary, right? It's something that you have to respect, okay? But in physics, it is the transition from one medium to another medium, right? So a very famous boundary that we see all the time is from like water to air, right? So this is not a bird's eye view. This is a cross sectional view, right? So if this is water, air, that's the boundary, right? It's the border, or in German, die Grenze, right? It's the border between that separates one medium from another medium, okay? And anytime I hit a boundary, some part of my wave will reflect, okay? That is huge, okay? If it's a really solid boundary, then the wave will reflect completely, right? That means like if I speak into this here, there should be no, if I put a mic right here, there should be no sound that is recorded because all of the sound should be reflecting off of here, right? So if I do that right now, right, why can you still hear me now, okay? There are a lot of different reasons why you can still hear me, but one of the principal reasons is a phenomenon known as diffraction, okay? Okay? Diffraction happens at the edge of a boundary, all right? So what boundary are we talking about now? We're talking about the cardboard air boundary, right? So this is my cardboard, right? And I'm sending a wave, right? And it's like, yeah, right? I'm sending a wave this way, right? All the wavefronts on this side get reflected back, right? So they go this way and then they go back, right? But the waves here pass by, okay? They keep going. But then how the heck do I hear it in this region, right? This is the phenomenon known as diffraction, okay? Anytime I'm at the edge of a boundary, right? So this is the cardboard air. This point acts like a circular wavefront, as if I am just, as if I'm just poking my finger here and there and here and there and here and there forever, right? So that's pretty cool. So then the wave ends up, quote unquote, bending around the wall, right? It goes this and then it goes like this. Is it really bending? No. It's actually just acting like a point source right on this edge. Now you might want to ask why that's true, right? There is a very famous principle, it's called Huygens principle, okay? And Huygens principle says that every flat wavefront you see, whether it's like in the ocean or if it's a flat sound wave or a flat broccoli top like I got going down here, right? So what my mom loves to do, she says, "Oh, Jinte, your hair looks like broccoli." I'm like, I know, it's my favorite vegetable, okay? Chris, if the wall is really, I'm gonna take a step back and answer Chris's question first, and then we can kind of move on. Oh, first of all, I need to make sure you know that this is not the bound. That's just some more wavefronts, right? That drew kind of weird. Okay, so I'll answer Chris's question first. If the wall is really thin, when your sound waves hit the wall, it makes the wall vibrate. And when the wall vibrates on the other side of it, it's creating sound, right? Just like the membrane of a speaker or the vibrations in your throat or anything like that. Anything that vibrates creates sound. Okay, so that's why. That's why it's, yeah, dude, yeah. And when you talk about sound energy or the energy required to produce sound, right? You should think of it as a type of kinetic energy, right? If I'm making sound with my throat, I'm converting chemical energy of my body to move my muscles to breathe a certain way, and then I use that energy to move the air molecules, right? In a longitudinal wave, the air molecules start going back and forth. I'm giving them kinetic energy, right? Yeah. And eventually, when my sound like hits the wall starts vibrating, and the wall has kinetic energy now. And then the wall will transfer that kinetic energy into the air molecules on the other side, right? Okay. Huygens principle says any flat wavefront is actually a collection of an infinite amount of circular wavefronts. So when you see this type of wavefront, right, what that actually is a bunch of circular wavefronts. And the reason they look flat is because all of these crests of those circles interfere with each other, right? Right, you see that flat wavefront there, right? Right, it's flat, right? It's flat here, it's flat there, and that's like what approximates like a flat wavefront. And the reason why it looks flat is because there's an infinite amount of these, okay? So why then does diffraction happen? Because the only thing that keeps a wave flat, right, is why is the wave flat here? Because there's a circular wavefront to the left and to the right of it. Why is it flat here? Because there's a circular wavefront to the left and the right of it. If you take away one of its neighbors, right, well then, doesn't that mean from this side onward that it's just going to be a circle? Like here, of course it's flat, right? But here, I can see a circle, right? Because there's nothing here to interfere with it, right? To make it flat, right? So it's just going to be the blue part, right? That's why diffraction happens around the wall, okay? Anyways, so let's keep going. Let's answer Dimon's question. Does the act of sound interacting with the edge of the boundary change the sound in any way? Yeah, it dampens it, right? For the example that Chris was saying, like if you yell at a thin wall, the person on the other side will have a lot of the higher overtones muffled and damped. They will not you will not cause the wall to vibrate at a higher harmonic. So your voice ends up being very muffled, and that's because all the high harmonics are canceled out. Reverb is a completely different thing. It's basically based on echoes, right? So it requires a larger space, and when I yell or sing, like my sound waves eventually hit a wall, reflect, and then come back to me. So I hear it much later than when I actually sang it. So that's what reverb is. And if the room has like good enough acoustical properties, like the reflection can get reflected, so then you'll hear your voice like 3 times, right? That's what reverb is. Okay. Hopefully there's no more questions about diffraction. It's how sound bends around a corner. That's like your cheat sheet in your notes. You can describe that. That's what diffraction is, like bending around a corner. But it's not really, right? All you're doing is eliminating the point sources to one side, which makes it look like a circle on that side, right? There's still like a circular wavefront here, right? But the reason why it appears flat here is because there's a bunch of other circles on this side, and they kind of all push it to be one big circle like that, okay? Huygens principle applies to any wavefront. Even a circular wavefront, all that is a bunch of mini circular wavefronts here, right? So, yeah, you can kind of look at it that way. No, because we don't view light as flat wavefronts. We look at it as like beams and rays. Yeah, a great question, Chris. All right, so let's move on to the second phenomenon that happens at a boundary, okay? Okay, the first thing you have to see anytime I hit a boundary, right, is the direction of propagation, right? Who that? Oh, I love you. So the direction of propagation okay? That's basically talking about the velocity of the wave, right? So for instance, if I have a bunch of flat waves going this way, right? Where's the velocity? It's always just perpendicular to the wavefronts, right? So that's my direction of propagation, right? If this is my boundary, right? Right, and then, yeah, sure, maybe I have troughs here, right, to get a better image of this wave, right? So, no, for all wavefronts, the direction of propagation is merely, it's always just going to be perpendicular to the wavefronts, okay? With that said, there is some vocabulary you need to know. When a wave is incident, all right, upon a surface, incident means it is put upon it, it occurs, right? It's how it enters. This is how it enters the boundary. Okay? Anyways, how it enters the boundary. So in this example, I would say it's incident here. And we describe its direction with an angle, but to write that angle down, we draw a normal line. What is this normal to? This is normal to the boundary. Right? So it's a normal line, and by that I mean it's a line normal to the boundary. Okay? And boom. There's my angle of incidence. All right? It's always relative to the normal. All right? Not that you have to worry about this year, but a really stupid question that's always given on the Regents is like, oh, like I have a wave and it's going here, and that's 30 degrees. What's the angle of incidence? And it's like 60, right? Because they're just testing whether you know to measure it relative to the normal rather than the boundary itself. Okay? It's not a horizontal vertical thing, right? Because guess what? If my boundary looks like this, right? My angle of incidence is not measured relative to the horizontal, right? So it's always just measured relative to the line that's normal to the boundary, which is this red line, okay? Now, two specific things happen when I hit a boundary, like in the middle and not at an edge, right? So diffraction happens at like the edge of the boundary, but if you hit like the middle of the boundary, two cool things happen. One, you reflect, okay? Anytime someone describes or enumerates their personal boundaries to you, that's a good time to reflect, okay, on how you are going to start interacting with that person in the future, how to be respectful, etc., etc. But also, waves reflect at boundaries, okay? And the only law that the waves follow, right, is that the angle of reflection. What do you guys think, huh? How is the angle of reflection related to the angle of incidence? This is just the law of reflection. Super simple. Super simple. Is equal, right? Yeah, so the angle of incidence is equal to the angle of reflection, okay? Which means for this example, the waves would be going this way, and then they would reflect and go out this way, right? Yeah, so they're going this way, and then they go this way, right? Waves aren't the only thing that follow that law, right? Most bouncy objects do as well. So if you play pool or billiards, any form of billiards like pool or snooker, right? You'll notice when you hit a wall, it'll always bounce at a very predictable angle. Okay, and here, yeah, Chris, it is true. We're not going to really look at the situation, but when I bounce this way and go this way, there is interference, right? There's constructive interference here, here, and here. That's where my crest meets a crest meets a crest. Is it a standing wave? No, because a standing wave happens when the angle of incidence is 0, right? The standing wave occurs when the wave goes this way and then it comes back this way. When it's happening at this angle, right, that's just a little bit different, right? Not really going to get into that. Okay, so, woo! We got 4 minutes to go over the last thing, okay? Woo! Last thing that happens is at a boundary, And I have some waves here, and they're going this way. Woo! Right, they're going this way. One, they do reflect, right? So some of the waves do reflect. I'm not interested in that. Some of the waves actually also pass through to the new medium. And there's two things that can happen here. I can either speed up, or I can slow down, okay? And we will look at both cases, okay? Crap, that's not the best picture, but whatever. Okay? And this is slower. Okay? If I use the formula to explain this, this is going to be V equals lambda times frequency. If I speed up in this medium, V is larger. Lambda must get larger, right? Frequency stays the same. Why does frequency stay the same from one medium to another? Let's put it this way, okay? If I'm underwater and I sing a note at 440 hertz, that means every second my throat is creating 440 crests in the water, right? Sarah, that is also another option, but it's boring. So we're only going to go over the more consequential ones where it's faster and slower, okay? But imagine, right, if I'm singing underwater and I sing at 440 hertz, I produce 440 compressions in the water every second. And they travel towards the air-water boundary. Well then, how many compressions hit the air-water boundary every second? 440. How many compressions are then transferred to the air every second? 440, right? So the frequency of a wave when it's traveling in one medium, when it enters a new medium, the frequency is going to be the same because it's just about how many things are created every second, how many things are entering the medium every second, right? So the frequency is remaining the same. I hope that's pretty clear, okay? So when I change my speed, I'm only changing lambda, right? And geometrically, the only way to do that, right, is to draw my waves like this. You see how these lambdas are much bigger now? Right, there's my lambda now. And here before was a smaller lambda. But what you'll also notice is that the direction of the waves have now changed. Now they're going, before they're going this way, now they're going this way, right? Likewise, if I slow down, if my V goes down, my lambda goes down. And the only way to do that in this picture is to draw them like this. Now I have a very small lambda, and you'll notice the direction of the wave also changed. It turned, okay? This is known as refraction. There's diffraction, reflection, and refraction, okay? Super important. Waves bend when they change speed, okay? The way to always remember this is with respect to the normal, okay? If I speed up, my wave propagation velocity, the direction of my wave, bends away from the normal. But it's going this way, now it'll go this way. It bends away when it speeds up. If my wave slows down, I bend towards the normal. Okay, I bend towards the normal if I slow down. Okay? And there is that's the one thing that should go in the notes, right? So speed up means I bend away. And the reverse for the slow. That should be the thing that goes in your notes, okay? I'm going to give you my most favorite analogy to use with refraction. Okay. Shout out. This one goes to all the real ones who play Mario Kart, okay? How is Mario Kart related to waves? Because your speed depends on your medium, okay? Chris, yes and no. We're going to go over that later, okay? Itamar, it's just the geometry of the whole thing. In Mario Kart, just like with waves, like the speed of your car depends on the medium, right? You're faster on asphalt, you're slower on grass, right? So let's pretend that this is grass and this is asphalt. And I have a car that's coming in at an angle, okay? So this is slower. And the car is going in this direction. Well, which way does a car turn if this wheel is slower? If my left wheel is slower than my right wheel, which way is it going to turn? Is it going to turn to the left or is it going to turn to the right? Put it in the chat. More towards the vertical, it'll turn left, right? So that follows our rule, doesn't it? If I slow down, I should bend towards the normal, okay? And likewise, if this is faster, right? You can imagine that the car will turn this way, right? If this wheel's faster than this wheel, it'll bend away from the normal, right? That's a really simple analogy to make with cars and stuff, but waves follow the same kind of behavior, okay? If you're still confused about like why they actually bend that way, feel free to look at a video. Okay, I can't find any good ones, but I'm pretty sure they're out there. Monday we are going to do something cool. All right, the last lesson on 2D waves. That's the end of our unit. Yeah, I'm gonna post some assignments. There are no real assignments this week, but there will be a test, like an assessment. I'm deciding it between like it being like a short essay or like a little mini project. I'm not sure yet, right? But it'll be due probably like next Friday, okay? And then we are going to start our unit on light on Tuesday, right? So get pumped about that. I gotta go now for my Regent students. Have a great day, and thanks for tuning in, guys. Some days I just feel really alone. You help me out. Are you having a final? No, I don't think so. I don't know. Bye.